In this video, we are going to discuss the difference between strength of material and rigid body mechanics, as well as discuss simple stress and do certain numericals related to that topic. So, first of all, the strength of materials deals with the relationship between externally applied loads and their internal effects on the body, whereas rigid body mechanics, that is the statics of dynamics, deals with the study of external forces of the rigid body. So, this deals with two things. That is externally applied loads and as well as internal effects. So, the externally applied loads means that the load acting on the structure, such as point load, it could be a point load, concentrated load, it could be a UDL, VDL, or an external movement. And the internal effect means the deformation and the strength requirement, and the internal forces that you need to calculate in order to calculate those internal effects, that is deformation and strengths. So this over here deals only with external forces. This over here deals with rigid body only. That is, change in shape can be neglected. That is, deformation are not taken into account. Calculations are not taken into account. We have to, in the strength of material, we have to calculate deformation-related characteristics, and we have to satisfy strength requirement. That is, the material, whatever load is acting on the material can withstand the load or not. We have to check that as well. So, to understand the difference better, let's look at this example. In the first, we can see that only the load is applied and there is a reaction to it, right? In the second, there's a load and there's a reaction, as well as we are trying to calculate the stress. The stress is basically the force per unit area. Whatever load is being applied divided by the area. This is the cross-sectional area. It will be circular, rectangle. Doesn't matter. If we are trying to calculate the stress, then it comes under the category of strength of material. Here we are just trying to apply conditions of equilibrium and trying to get this reaction over here because of this load on the column. So this is related to rigid body mechanics, statics and dynamics, and this is related to strength of material. So let's discuss what is stress. The stress is force per unit area, but keep in mind that force is the internal force we are talking about here. It can be written as sigma is equal to P over A. This is a sigma letter, Greek lowercase letter, and this sigma, when we calculate the stress using this formula, is basically the average stress. That is the stress on uniformly applied, uniformly induced on the cross section. In reality, the stress at different points in the section is different. So, but we, by using this formula, we calculate the average stress. We can see over here that on this cross section, the value of stress is same for all points. Well, in reality, it's not the case. So let's move forward. Depending upon how the load is acting on the structure or a member, there can be different kind of stresses, different nature of stresses. One can be, if the load is applied normal to the surface of the cross section, normal to the cross section, or perpendicular to the cross section, it will be normal stress. If it's produced due to bending of the material, then it's a flexural stress. If it's produced due to torsion or twisting of the member, the stresses induced will be torsional stress. If the force is applied such as it is parallel to the cross section, then shear stresses will be induced in it. So before moving on to normal stresses, let's discuss the difference between the pressure and the stress. Remember that pressure is externally applied and stress is internally induced. It is internally produced. So we know that we can't physically apply a point load onto something. It's basically we apply a pressure on top of the surface, then we convert it into a point load. So how do we convert pressure into a resultant P load? We just have to multiply pressure with the area, so we get the resultant P load. In order to calculate stress, to find the stress over here, we need to find this internal force that is acting on this cross section. How can we find this internal force in this circumstances? We can do it by applying the condition of equilibrium, that is summation of Fy. This is externally applied force from pressure. We obtain it from pressure, and then by obtaining this P, we can calculate the stress. This is internally produced. This is an internal force, and we can calculate internal stress by internal force. By calculating internal force, sigma is equal to P over A. So what I'm trying to say is, when calculating the stress, we need to find the internal force. We are interested in internal force, not this externally applied force, right? So let's move forward. Now let's discuss normal stress. Normal stress, as the name indicates, that the force is normal to the cross section. As you can shown in this figure, we have a cylinder and we have a force which is perpendicular to this cross section. It's a circular cross section. Now the normal stress can be of tensile as well as compressive in nature. So we can see over here that there are two bars and there are two forces being applied over here in opposite directions. One is downward and one is upward, and we can calculate the reactions using the condition of equilibrium. And we can see over here that the bar 1 is being elongated and the stresses produced here are tensile stresses due to elongation, and the stresses produced in the second bar are compressive in nature. So both of these tensile and compressive stresses are basically normal stresses, right? So now let's discuss the unit. What is the unit of this stress? So we know that force can be represented by Newton and area can be meter square. So this could be one of the unit of the stress Newton per meter square. It can be represented with kick per foot square or kick per inches square, lb per inches square. It depends. And we know that 1 Newton, some important conversional units, 1 kip is equal to 1000 lb, 1 Newton per meter square equals 1 Pascal. Okay. Now let's move to a problem. Okay, a composite bar consists of an aluminum section which will be fastened between a bronze section and a steel section. So there's an aluminum section, bar, and bronze bar and steel bar. Axial loads are applied at the positions indicated. Determine the stress in this section. So these are the axial loads applied at this point, and this point, and this point. So we have to determine the stress in each section. Okay, so first of all, we need to calculate the internal force, right? So there will be 3 internal forces, one for this bar, and one for this one, and this one. So in order to find internal force, we need to draw the free body diagram. So I will, in this case, I will have to cut 3 sections because there are 3 different materials. Remember, to calculate internal force, we have to cut a section. So first of all, I've cut a section. We will consider number 1 section, and we need to find this force over here, FPR, right? We can do that we can calculate this force by applying conditions of equilibrium. Summation f of x equals to 0, and I have taken rightward, it's positive, and this in this case is going leftward. So this is minus 4000 plus I've assumed this force to be rightward. I could have assumed it to go leftward, but I have taken it as rightward. It doesn't matter at all. So it matches this sign conversion. So it matches this sign convention, and this will be close to FBR. FBR equals to, and we can calculate from FBR from here. FBR equals to 4000 lb. Similarly, for second section, for 2 section, we can see that either you take this whole portion, leftward portion of the section, or rightward portion of the section. Doesn't matter at all. I've taken the leftward section and and I've taken all the forces applied axial loads that were given in the question, 4000 and 9000 lb, and then I have assumed I assumed the direction of FAL took the rightward. It doesn't matter whether you take it leftward or rightward. Doesn't matter at all. It won't affect your answer at all. So I've again taken rightward positive. Summation f of x equals to 0. Force summation of forces in x direction is equal to 0, and then I can see that it's opposite to my sign convention. So this is minus 4000 lb, and this will be positive 9000 lb. This force over here. Now what about this force? At first I had taken this sign convention. Then according to this, it's positive f plus FL equals to 0, and now I can calculate FL from here. So FL comes out to be minus 5000 lb. So the minus sign indicates that the direction which I assumed earlier was not the right one. This is the right direction. So you can just circle it and mark this direction as right one. Okay. Now let's move to the third section. So we have this. So we have 3 section over here. Now it doesn't matter. You take the leftward portion of from this section. You can take the left side of the figure, or from this section you can take the right side of the figure. So to avoid complications, I have taken the right side this time. See, so I have taken right side portion of this figure. So basically, if it's steel material, so I represented, I denoted this force with FST, and now to calculate FST, again, summation f of x, I've applied condition of equilibrium and taken rightward sign as positive, and then I have got FST equals 7000. Now I have all the forces, FBR, FL, FST, internal forces in each material. Now I can calculate stress. We know the stress in measurement form can be written as P over A. So for sigma bronze equals to FBR upon ABR, area of bronze. So this is given in the question, 1.2 inch square, and this we have calculated FBR. This is the internal force. We have calculated internal force for each and every material. So divided by the area of that section, you will get the force. You will get the stress in each material. So this comes out to be positive. This is now. How do we know what is the nature of that stress? Okay, how do we know that? So let's look at this. I have marked sigma bronze as tensile. So let's see. If the force is such that it's moving away from the cross section, one cross section, then it's tensile in nature, right? If the force is such that, we know that if the force is such that if it's moving inside the cross section, it's such as in this case, it's going inside the section, so it's going to be compressive in nature. We know that at first I assumed this force. to going rightward. But after that, when I did the calculation, there was minus sign indicating that this force, the direction of the force that I've indicated, I've assumed it wrong. So this is the right direction applied in the section. So we know that if the force is going towards the section, that is compressive in nature. If the force is going away from the section, it's positive. So in this case, again, the force is at this section, 3-3 section, FST is going inside the section, so it's compressive in nature. And if you look at the whole figure, it's going to be difficult. In this sense, we can say that it's elongating this material, and in this case, we can say that it's compressing this material, so this would be compressive in nature. But here we cannot determine by just looking at it. So you have to look at the direction of that arrow. Is it going inside the section or outside the section? If it's going inside, it's compressive. If it's going outside, it's tensile in nature. Okay, another question related to nominal stresses. Block of weight W in figure 110 hangs from the pin at A. The bar AB and AC are pinned at the supported B and C. So these are the bars they are talking about torsion, and they are pinned at A and B and C. So the area of the areas are 800 millimeter square for AB and 400 millimeter square for AC. The area is given for these bars, these two bars, and neglecting the weight of the bar. They are not considering the weight of the bar. Find the maximum safe value of W if the stress in AB is linked to 110 megapascal and that in AC to 120 megapascal. So they have, in this case, in this question, they have given the stresses and they are asking what would be the value of W that the material wouldn't fail at all. The material, the bar AB and the bar AC wouldn't fail. What would be the safest value of W? So in order to calculate, we have been given sigma AB and sigma BC as well as A. Both these things are given. The stresses and areas are given. We have to calculate W. So how are we are going to calculate W in this case? We are going to represent W. We are going to represent FAB and FBC in form of W, and then trying to calculate W from both of these, from this one, this formula here as well, and this one here as well. Then we would take the smallest value of W from both of these formulas, right? So first of all, we need to draw the free body diagram. So we know that there will be force in this bar as well as in this bar. I represent the force in AB bar as FBA, and in this bar FAC and W. So this is the free body diagram. So in order to represent the weight in the form of FAB and FBC, I need to determine, first of all, I need to determine the components of these forces. For FAB, I have been given the angle 40 degree with respect to the horizontal x-axis. In order to calculate the component of this force, we know that the component adjacent to the angle 40 degree would be cos 40, and the component which is not adjacent is obviously going to be sin 40. You have to just remember the trick that whichever component of the force, such as FAB in this case, is adjacent to the angle 40 degree, it's going to be cos 40. It's going to be the component is going to involve the term of cos. So here as well, to find the component of this force, there are two components, one in x direction and one in y direction, one in x and one in y. So if you want to determine the component in x direction, we know that the component adjacent to the angle is going to be of cos. It's going to involve the term of cos. So this is going to be FB cos theta, and the other one obviously is going to be FB sin theta. If this is cos, this is going to be sin. So if you draw this in one single diagram, we have something like this. These are the AB, FBC, and all the components in y direction as well as in x direction. So applying the condition of equilibrium in y direction, we have three forces in y direction: FAB sin 40, FAB sin 60, and W. FAB sin 40 plus FAB sin 60 minus W. I have considered upward as positive. I've taken upward sign as positive. Then FAB sin 40 would be positive, and FBC sin 60 would be positive, and this would be negative. Solving this term would result in this equation. Again, applying conditions of equilibrium, but in x direction this time. So there are two forces in x direction: this one and this one over here. So after solving it, you will get something like this. After solving it, you would get something like this. So you have two equations. Now you can simultaneously solve it, this one and this one. You need to simultaneously solve it, right? And you will get something. You will get the value of FBC and FBA. Remember, there are two unknowns, right? There are two unknowns, FAB and FBC. If you look at these two equations, we have two unknowns, FAB and FBC, FAB and FBC. W is not unknown; it's a constant, right? So When you solve this equation, two equations, you get FBC equals to 0.7782 W and FAB equals to 0.5079 W. Now, just substitute the values of FAB and FBC in these formulas and calculate W from here. We know that we have been given the stress of 110 megapascal for AB and area 800 millimeter square, and you can calculate W from here over here, and then W comes out to be from the condition of stresses and area given in AB. W is equals to 173.26 kilonewton, right? And in this case, sigma BC equals to 61.65 kilonewton from the conditions of BC, from the parameters given in BC. So you, in the end, you have to compare both of them and choose the smaller one. Now, why do we need to choose the smaller one? Why not the larger one? Let's say, for instance, if you take 173.26 kilonewton as a weight for this configuration, you take W equals to 173.26. Now, what would happen for sigma BC, for the bar BC? It can take only 61.68 kilonewton. It cannot take more than that under these circumstances, under these parameters given, under data given for sigma BC. So we have to take the smaller value. Otherwise, the material AB can withstand, the bar of the material AB can withstand this load, but the material of the bar cannot withstand more than 61.68. So you have to take the smaller value. So that's the reason. If you have any kind of questions related to this topic, you can write it in the comment, and I will get to it as soon as I can. And you can also email me. My email is given in the description box. Thank you.